month of origin of homochirality, and I would like with very great pleasure to be here, and in particular when I see Robert, I remember your last lecture in Barcelona. You were lecturing in Barcelona. There was a person in the audience that he has to replace somebody, he has to substitute someone, right? And this person actually was believing that the lecture of Robert was the lecture of the guy who was supposed to give the original lecture. At the end of his talk, you come with some questions asking you about something about astrophysics, if I remember correctly. It's a problem. But I want to find this as a kind of an indication that the field of chirality is so broad that we have so many languages, we have so many ways to tackle this problem of chirality and the origin of homochirality. But I like to see this audience, such a broad audience with different views. I would like to express one of our experiments that we are planning for a number of years, and which comprise, I believe, some effects of Frank models and other systems that are built mathematically, and maybe that we can encourage some of the theoreticians to try to use this. As I say, we are very interested in starting from glycine, which appears to be the most common amino acid, which was formed in the Meir experiment, and also in the Wachtenhauser experiment. I mean, glycine appears to be the major amino acid which can be formed in comparison to all other amino acids. And the question was whether this simple molecule of glycine, which is non-chiral, the name of the single amino acid which is non-chiral, and whether this amino acid could play some role in stochastic linear symmetry breaking. And what was our challenge was to go from this particular amino acid, to go to peptides, and to homochiral peptides. And studies that we are currently interested in is to try to see whether we can go from such simple molecules to build up homochiral copeptides. And finally, something in the next future, to try to find among these copeptides, homochiral copeptides, which have been generated from racemic mixtures, to play some catalytic roles. The first of the master systems, which might be very prebiotic, should probably be some kind of copeptides. So the first problem was actually how to start with that, and this was the problem of crystallization. And the stages that we went through from the very beginning was, the first part was absolute asymmetric synthesis, rule of Russell, which I shall discuss. I don't know whether the term absolute is correct. I prefer today to call it spontaneous asymmetric synthesis in comparison with the spontaneous resolution of Pasteur, if you like. Reduction of symmetry of crystals. And I think this is a very important, extension, because reduction in symmetry, and if you look on the old days, still I think the 80s, people believe that if you like to break symmetry, mirror symmetry by crystallization, you have to confine to one of the 65 enantiomorphous space groups. A lot of work has been done on quartz, a lot of work has been done on sodium chloride, and people are looking for achiral molecules which can crystallize in enantiomorphous space groups. And I think that in the course of our studies we have made an important extension. I find this a very important extension, that by investigating the mechanism of the formation of mixed crystals, we come to a very general concept that you can mix crystal, centrosymmetrical mixed crystal, I mean the centrosymmetrical host can be converted into an enantiomorphous mixed crystal. And I shall see this by kinetic control process. You can convert centrosymmetrical crystals into enantiomorphous crystals, and therefore we can extend the repertoire of crystals that we can use for mirror symmetry breaking, also to the centrosymmetrical crystals. We shall see how important is this when we come back to the crystal of glycine. And then this will be an application to that will be glycine RS alpha amino acid system. Then the next point will be something that is crystalline aggregates, which are formed there with the interface. And this is something that came out from our attempts to investigate this particular system, but we went together with some Danish colleagues, Professor Jens Nielsen and Christian Kerr, maybe you know.
Ja. Peter Nielsen, you mean?
Know that?
Peter Nielsen.
Yeah,
Yeah.
yeah. And trying to understand the organization of molecules, amphiphilic molecules of their water interface. For a number of years we were interested in what we call crystallography in 2 dimensions and the air water interface, and to see the importance of these crystallites which are formed in their water interface, how they can operate as very embryonic nucleating species which are important for amplification of chirality. Then we shall go to the problem of crystal nucleation, and we shall see how we can design specific enantioselective inhibitors for crystal nucleation, which also can be used in the mechanism in the experiment, which I would like to express in this way of symmetry breaking. And then spontaneous segregation of racemic and non-racemic alpha amino acid at their water interface, which studies what we call spontaneous segregation of racemic and alphamorphous domains at their water interface. And then afterward, to convert these amino acids into homochiropeptides to racemic amino acids at their water interface. We have recently demonstrated that racemic triple beta sheets can operate as very important templates for the generation of homochiropeptides from racemic alpha amino acid in liquid solution. And then finally I shall complete with some conclusions and cannot establish this technique.
Now, when you say homochiropeptides on that previous
Yeah,
thing,
homochiropeptides.
are you talking about taking racemic mixture of alpha amino acids and making a racemic mixture of chains, each chain of which is
We can make
homochiral?
racemic mixtures here.
Or are you talking about choosing one of the enantiomers to make a
No, we are taking racemic mixtures, and when I come to the last experiment we're doing, I take mixtures of 4 or 5 racemic mixtures of, let's say, alanine, tyrosine, alanine, leucine, putting them in water and polymerizing them, and then we go into poly L and poly B. But if you take oxidation model, you will see that in these systems, in principle, you can envisage that the mixtures are not completely racemic. We might have some kind of
once you've done the first, then you set up the possibility of the second.
Or if you put some initiator into the system, which is kind of initiator, and we shall see this part, that can be. All right. So the model that we started a long time ago was actually what we call the Calvin model. The Calvin model said that before that we were inspired by the Calvin model. This was study that we started in, I think, the early, long time ago, 20 years ago. When you take, let's say, a system which is either chiral or fastly racemizing system, okay, it may be sodium chloride if you like. You can take silicon, Nordic quartz, but you also can take some very fastly racemizing systems, like if you take epsilon caprolactam, that synthetiatis is used, and then what happens is that if you have a reaction on this part, we have a process with that, then you generate a species which is chiral. And if this species, which is chiral, and is a catalyst for the process, and the rate of this catalyst is much faster than this process of reactivity, you can in principle envisage the formation that you can drive the entire racemic system into a product of single elements. Sometimes you can go to the left, sometimes you can go to the right. Okay, this is the Calvin model. I think the first one we just discussed this with Gunther an hour ago. So what we saw that problem is that in principle in crystallization you can materialize, if you like, experimentally the Calvin model. And this was done to say if you have a fast racemizing system, if you crystallize it, and this is what Havinger long time ago performed. This was the first experiment, but that was followed by Powell and others, that what Kurt Mischel would say, this is a total asymmetric transformation. People today are taking new terms of that, but the old term for that is total asymmetric transformation. You can convert a racemic system into a crystal of single elements if you perform the crystallization under controlled conditions. Okay?
Which amino acid is on the large, gigantic, industrial scale following Calvin's model? I think it's aspartate.
No, aspartic acid it doesn't work because aspartic acid is a racemic crystal. I made glutamic acid. Glutamic acid because glutamic acid has two polymers which are enantiomers. Okay? So what we scientific problem is that we wanted to do this. At the time we were interested in what we call crystal engineering. I worked with Gerhard Schmidt, and the person who coined the term crystal engineering. And the third problem was say we wanted at the time to design an experiment. So people today are using the term crystal engineering just if they find some kind of interaction with crystal, they call it crystal engineering. This is not crystal engineering. Crystal engineering is like synthetic chemistry. I have a target. I want to achieve something, and therefore I have to plan, and I have to force this molecule to force it to crystallize in a given crystal which is appropriate for my purpose. Okay, and this is what is crystal engineering, right?
That's the hard definition.
It's very hard definition, but we had it actually, and we were, at the time we said, okay, I want to have a molecule, because no one today can predict the crystal structure of a given organic molecule from the molecular level. John Mattock said this is the scandal of the 20th century. Because no one, this is the editor of Nature.
It'll never be solved.
This is actually what it?
It'll never be solved for the same reason that you and I discussed about chemicals.
Some people believe they do. If Dr. Schrager, I will tell you that it's possible. If you take some others, that very small difference interaction can be a problem, but today I don't think that if I give you a molecule, you cannot give me the crystal structure. We can do something. We treat some experiments on this. We get to some of our friends the molecule and the crystal structure, and they return us with the crystal structure. But if you just give them molecules without the crystal structure, they will give you a large number of crystal technical crystals. But Angelo Gabezzotti from Milan will tell you, never like what you say. It will be never possible to predict the results. So what we wanted at that time was the following. We said, let us take a molecule which is non-chiral, because this molecule has a mirror plane. And if it has a mirror plane, this molecule is non-chiral. And at that time we thought about crystals which are enantiomorphous. If they can be designed such system which will crystallize in a specific crystal structure, such that the molecules in the crystal will be related only by translation. And if the crystal is related by translation, this is a polar crystal, okay, it's an antimorphous crystal, and where the double bonds between the one which is Y and X will be in good proximity for activity, this is 4 Anstrup, this is what Gerhard Schmidt actually in the early days confirmed, and we knew a little bit about the system, therefore we wanted to go to this particular system. If they are related by 4 Anstrup, then if you align such a crystal, you're going to generate a product which is chiral. The dimers are chiral. Okay? You see that? Because this molecule does not have a center of symmetry. There is no center. This molecule is not symmetric. Okay, this molecule is chiral. Enantiomeric to this one. Okay? If you get the trimer, tetramer, this one. Hasegawa did some polymerization of these dying systems. If you get this problem, this molecule has only a quasi, if you like, translation of symmetry. Okay.
And
Is that clear?
Generated by energy, by radiation or?
By radiation, we just irradiate the crystal. Now what you have to do it, we found ways how to crystallize this crystal under very controlled conditions. We grew this crystal very carefully. And there are some other reactions. I think today these absolute asymmetric syntheses are very common. There are actually Toda in Japan, Schaeffer in Vancouver, and also in this country, Mike Atkinson Mike Atkinson.
Oh yeah, in Gothenburg.
Yeah. Also. So this is, I think now there are more than 3 dozen of systems that are brought up similar. But this is one of the first ones. Together with Mike, with Frank Chapon, Donald Chapon, and from Buddy Greek, and others collaborated, Gerhard Schmidt, and Frank also. Well, now, as I pointed out, what we wanted to be stick to the Calvin model. And what the Calvin model says is the following. You start with such a monomer. You crystallize by chance one crystal. And if you crystallize by chance one crystal, you irradiate the crystal. You change the temperature, you melt. But now in the crystal, in the solution, you have homochiral products. And our question at the time was, how this product, which is present in the solution, in the milk, if you recrystallize, how this molecule, which, if you like, this crystal has transferred some information to this molecule, because there is a correlation between a dimer in the crystal with that particular molecule, a trimer in the crystal with that particular molecule. You have transferred some structural information from the crystal to the molecules, and the question is, if you melt and these molecules are stable upon melting, what will happen if I take a fresh compound of this one, and now I can recrystallize it in the presence of these dimers which have been generated spontaneously in the first experiment? Is that clear? Because this is exactly what the Calvin model says. I take this molecule, I crystallize it, I form a product, and this product now catalyzes the formation of the third product, which is the nucleation of the crystal. Okay?
So you did that.
Okay?
This was done?
Yes, I will just come in a moment. Robert, is okay? Okay, because I will come to you because of this problem of the... So what we wanted is that we have a catalytic process, which this product will catalyze the nucleation of that particular crystal. And my idea at the time was, since these molecules are very rigid, I thought that they might serve as some kind of nucleus around which you would be able to get the crystal of the same elements. Okay? But when we performed this experiment by taking this starting monomer and crystallizing this monomer in the presence of a dimer, which we isolated, we were very happy to get an asymmetric induction. We got an asymmetric numeric axis. But what happened was very unexpected. The dimer, which we got in crystal plus, induced somehow the precipitation of the crystal minus. And the dimer, which was formed in crystal D, induced the precipitation of crystal F.
That's not surprising.
Okay. Now today, does not surprise us as well.
I mean, it seems surprising, but when you think about it, it's not surprising.
The question is how you think about the system. Now, at the beginning, we thought that these are rigid molecules. They will create like a crystal, induces the crystallization of its own. But then we found that even slight changes in the structure of the dimer vis-a-vis the monomer, then we have a kind of a process. And then we decided to investigate this process in general. And what we found was the following. We tried to use morphologies of crystals. What is the morphology of crystals? What defines the morphology of a crystal? The morphology of a crystal is defined by the rate of growth of the various faces in a different direction. You know that you can grow many crystals that have the same morphology, unless you eliminate the effect of the environment. And then we say the following. If you're dealing with organic molecules, which belong to space groups which are low or close symmetry, like clinic, non-clinic, or rhombic, then you have various faces that delineate these crystals. And therefore the structure of the non-symmetry related faces are different. And you can deduce the structure of these faces from the crystal structure of the system. If, of course, you can induce after that king steps and more problems to make more and more system. And then the point is that if we are speaking now in terms of surface recognition for the molecules of the environment, we can believe that this dimer, which very much resembles that of the crystal structure, can be attached only to some specific surfaces of the crystal, and that by being attached to some specific surface of the crystal, it can change the morphology of the crystal. Because if you have a molecule which can be attached to this particular surface, and there is another group which perturbs the growth in this particular surface, the surfaces of the affected crystals, or the affected faces, will increase now. So you can measure the surfaces of the various crystals that you have by adding some specific additive into the system. And from this morphology, you can in principle deduce some information about the binding of the molecules to the various faces of the crystal. Okay? And this was what actually, this is unaffected crystal. rate of growth of B is very large as compared to A, therefore this phase is less expressed than this one. And then after that, you have stereoselective addition to some surfaces B, and then what will happen finally, the B, the surface of the B will be much larger as compared to A. So by studying crystal morphology, we were able in principle to go to learn something about the mode, how molecules interact with the various phases of the crystal. Okay? Any question?
Yeah.
Okay, we have any
The other way
question?
around?
What is?
Confused here.
Just a moment.
Rate of B is bigger.
Yeah.
Yes, in the left one.
Yeah, within A is larger than B.
So smaller.
Because these phases have been affected,
Yes.
and if they're affected now, they grow slowly.
Yes.
If the phase grows slowly, it's much more expressed, and then what happens is the surfaces of these crystals are much more expressed as compared to the ones which are not affected. Okay? And this is now a very general concept, because you can go to any crystal to look on the structures of any of these crystals, see how the structure, the phases are composed, and you can compose now, you can design a molecule which is composed from two parts. One part which will bind non-selectively to some surface, but not on another, and the other part which perturbs the growth of this particular surface. And this is very general. We were able to manipulate our crystals as we want. We have benzamide, any crystal, actually there is no exceptions, because this is something which belongs to binding of interaction between molecules and the environment, including the role played by solvents. We were able actually to explain how a solvent can change the morphology of the crystal. And the first example, in order to learn something about it, we took a conglomerate. We took the Pasteur experiment, the first experiment when you have spontaneous resolution, and what Pasteur was doing was picking up crystals, looking on hemiagonal phases. And they say, if I take such a conglomerate, and I add, let's say, a molecule which is S prime, and this S prime can impede the growth of S and R, we shall get different rates of crystallization, and even more, I can modify the classical experiment of Pasteur by just looking not on different hemiagonal phases, which is a very rare effect, but I can look on different morphology between the R and S crystal. And I will just show you one example. If you take the threonine, it's crystal P21212, you cannot differentiate between the L and the crystals. But if you add any other amino acid in the solution, what you find, first of all, crystallized beautiful crystals. If I put, let's say, L glutamic acid, first crystallize D threonine, and after that you get powder. And if you separate the powder from the crystal, you see the powder is the L, and the crystal is the D. Okay, so now this is something which is very clear. This is, you take L with L, you see, depending how much you agitate, 1%, 2%, you can see that the crystal can be converted into a simple powder. And then if you take L-threonine with L-glutamic acid, you get a part. And if you take asparagine, we took 6 crystals, we glue them together, one of them falls apart, but if you take the 3D in the presence of L-glutamic acid, they are completely different morphology as compared to the other. So we were able to modify the Pasteur experiment of separation of conglomerates. But now the problem is here that the question of how mixed crystals are formed. And therefore I shall try to come with that idea in order to extend this concept from enantiomorphous crystals to racemic crystals. Now if you go to the computer, you can see here a crystal where all the molecules in the crystal are residing in ecoenergetic environment. Okay, so now if you're a computer person and you want to see how a mixed crystal is formed, you pick one molecule, put another one. You will pick these molecules in any side equally well, right? But the problem is the following. If you go to the mechanism of the formation of a mixed crystal, then what happens is the molecule first has to be attached to the surface before being occluded by an overgrowth on this particular surface of the crystal. Therefore, if you take a crystal which is centrosymmetric, and you grow it with a guest molecule, in principle, what you should be getting a mixture of sectors, where each sector, because of kinetically controlled process, each sector should have a different composition. Because if the surface recognizes this molecule here, actually they should be attached only to the azure, or they could be attached here to the azure or to the azure group here. Here they will be attached to the green. They will be attached here to the green here. They will be attached here to the yellow here. They will be attached here to the red here. So in other words, if you grow a centrosymmetrical crystal in the presence of another molecule, you are going to get actually an hybrid structure which is composed from different crystals, from different space groups. And these space groups will be lower than that of the bulk crystal. They will be determined by the structure of the surface through which this molecule has entered that particular sector. Okay? And we've done an experiment of this kind. We've taken cinnammide as a molecule which is non-chiral. And growing in the presence of thiophenylacrylamide, because thiophene and benzene are very similar structures. Okay? And what happened is that sulfur is an heavy atom. We have also labeled one of the molecules with deuterium. We sectored the crystal. We went to Brookhaven. We measured the crystal structure of each one of these sectors at liquid helium temperature, and we found that the space group of each particular sector is different. But we could predict from the crystal structure. Okay? We also performed some chemical reaction on that part and on that part between two achiral molecules which have crystallized together, and this one gave a positive dimer, this gave a negative dimer. Just confirming the fact that you can reduce the symmetry of a centrosymmetrical crystal by growing this particular crystal in the presence of an additive material in the system. Okay? Please ask questions. Okay. Now, I would like to explain the next experiment. Just let me give you the result first, and then we shall try to decipher the effect of the experiment. We are taking a solution which contains, let's say, glycine 10 times more as compared to the DL amino acid which we have in the aqueous solution. Okay, you have all the amino acids except proline. We shall see for the reason why proline doesn't participate in this game, but all the other amino acids. And then you start crystallizing. For example, if you start crystallizing, let's say you add 1% of one of the other amino acids in excess, just for the sake of discussion, but this experiment can also happen without this having. And then what happens is that crystals crystallize in the air-water interface here, and we added some of this lysine, as we say, all the amino acid, which is yellow. And if you have the R-leucine, 0.5% of R-leucine in the solution, you find a crust of crystals of lysine which contain all the alpha amino acids in that crust. We could do it by HPLC, and we saw that all the amino acids are in that crust. If you have the S-leucine, you find all the crystals, but they are of opposite. They don't contain the amino acid inside. Okay? They don't contain, in other words, one can contain the L amino acid, the other one can contain the D amino acid. And since we have added a very small quantity of the marker which does not affect the crystallization, you see that L lysine and DP can go into this crystal but not into this crystal. And if you go to the HPLC of the system, we have selected here 3 amino acids just for the sake of clarity of the HPLC which we've done in the chiral column. If you take, let's say, L-leucine into the system, what you find, let's say, you find that you get in the crystals, which are formed in air-water interface, only para-hydroxyfluid lysine, D-glutamic acid, D-methionine, but you don't find the amino acid. In other words, what you have a mixture of DL amino acid. You can put a small excess of one, and I shall show you later on that it's not necessary to do that. But if you want to get a reproducible experiment, you put quantity, you bias the system by small quantity. It's 1% of the entire mixture with amino acid, and then you see that this forms a crust, and there was an interface which contains either L or the amino acid in the system. Now the question is how we can explain this effect, how we can decipher the various factors which are operating in this particular experiment, which allowed us to really to separate spontaneously the amino acid DNA. And there was an interface, and of course, what happened in solution is of opposite values.
So then what makes them look so different, the two crystals?
Well, I shall try it now to show that. Okay? So the first thing that we are going to do now is glycine. And I say glycine has three polymers. The most stable polymer which crystallizes from water is centrosymmetric. Beta form is metastable, it's polar, antimorphous. Gamma is metastable. It's stable, but doesn't appear in water. You have to have special conditions, high pH, low pH. But if you crystallize glycine in water at room temperature, and pH 5 to 6, 7, you get always the alpha form of glycine. Okay? Now, I discussed the aspect of reduction in symmetry in crystals. Okay? So let us analyze the structure of this alpha glycine crystal. It is centrosymmetric. It is composed from layers. And this is the R. If I replace this hydrogen by deuterium or by another group, there are these two hydrogens which Kurt Mislow. You mark this PhD with Kurt Mislow. If you take this one, they are in solution. They are what's called enantiotopic. They are related to each other by middle pair. But in the crystal, these hydrogens occupy different positions in the crystal. Okay, and therefore in the crystal, this glycine molecule is chiral because the two hydrogens are diastereotopic. Okay. Now, if you take the next layer of glycine, is related to the first layer by center of inversion. Okay, and therefore it has exactly the opposite handles as the first glycine. Okay. If you go to the third layer, you can see again it is related by two-fold screw axis. They rotate and then move. And then you go to the first one and you build the unit cell. Okay? So you have layers of R and layers of S, layers of R, layers of S, and so on. So what now happened? We spoke about reduction in symmetry. What happened if I grow this crystal in the presence of any one of these alpha amino acids except chlorine, right? All of them have this tritarionic species. Okay? And in addition to this tritarionic species, they have this group which protrudes from the surface, O1O surface, from the crystal. But the R molecules can replace only molecules in the R layers of the crystal. Because would such a molecule come from that direction here, this surface will not recognize the R molecules. On the other hand, the S molecules can come inside from the other side. So if you grow this crystal in water, in pure water, in the presence of DL amino acid, the DL amino acid will undergo spontaneous resolution within the crystal of glycine itself. Okay? Is that? Okay. So this is what we have here. We say we can learn about morphology. If you grow these crystals in pure water, you get bipyramids. Okay? If you grow these crystals in the presence of R, you get an antiomorphous pyramid. If you go to with the S, you go the other one, and if you go with DL, you get a plate. Okay? There was a very important finding here, which I don't know belongs to the origin of pharmacology, but belongs to another question. When Pasteur did his classical experiments, he was able to tell that the species which compose the tartaric acid are composed from an antiomorphous species, they are chiral. But he was not able to tell the absolute configuration of the molecule from the crystal morphology. And even when Bragg and Bragg came out with the X-ray, because of the Friedel law, they were not able to do this by usual X-ray crystallography, and therefore only Byford in 1948, when he applied anomalous scattering, was able to tell what is the absolute configuration of the amino acids, okay, from this anomalous scattering. But here what we have, because if you go to the centrosymmetrical crystal, and you know the absolute sense of chirality of each one of the two surfaces, you know that. Because you don't have two pairs, you don't have bifid pairs like in anthropomorphous crystals, you have just one. Would you replace two molecules, you're going to get a different crystal, which you can determine by actual crystallography. And therefore, by comparing the morphologies of these crystals, we were able to tell the absolute configuration of the R and S amino acids on an absolute scale. This was one of the outside problems of that. And then what I say here, we are getting a spontaneous resolution of the dual amino acid within the crystals. If you grind part of this crystal, you get R-glutamic acid, S was missing. If you grind the green part, you find that the S-glycine is there. And if you grind the entire crystal, you find both elements into the crystal. So the next step, of course, is what happens if you grow that crystal on the interface? If you grow that crystal on the interface, you're blocking one of the faces. You're blocking one of the faces. And you're exposing only one crystal, one face. So if you grow a crystal of glycine in the presence of dual amino acids on its interface, you're converting the centrosymmetrical crystal of non-chiral molecules of glycine into a mixed crystal which contains amino acid only of single elements. Okay? So in this case, what we have done, we have now extended the idea of using enantiomorphous crystals, which are only 65 out of the 230 space groups, to centrosymmetrical crystals which can be used as mixed crystals for the formation of, reducing the symmetry and formation of an enantiomorphous system. And I think that this one that we proposed a number of years ago. More recently, there were two studies, one by two geologists, the person that organized the Golden Conference, what is his name? The person that organized the Golden Conference in Ventura. Bob Hazen. And the Hurrell actually extended this idea to calcite crystals, because they grew the calcite crystals with aspartic acid, and they found some interactions between between aspartic acid and calcite. But this was exactly the same concept that we elaborated long ago, both for many systems, not only glycine, but gly, other dipeptides and other systems. So this was a very general concept that we had, and they have actually demonstrated this also operates in some minerals, which are of course of importance for example, if you etch the crystals in the presence of R amino acid, this phase O1O is really, you can see etching, very strong etch pits. And if you do it, this phase in the presence of the R amino acid is not etched. So also etching teaches us something about the process of interaction. This is not so simple, but actually this is one of the results in the system. So the question, of course, now is like the question of quartz, or like the question of all the other crystals. If we take an anthropomorphous crystal, sodium chloride, if you like, everyone, you have one crystal, and you want to see that the next one that will grow will be of the same endedness as the first crystal, right? And there are different models, like McBride's, from the Pudi, of course, that presented that, and McBride that presented the mechanism that will break the crystal into many crystals, then you can have an autocatalytic process in the formation of the system. Now the question that we ask ourselves, what is the analog for such an amplification, of the catalytic amplification in the centrosymmetrical crystals, where let's say one crystal has assumed a certain orientation, and the question is how you transfer information from the first crystal to the new freshly formed crystal to be with the same orientation as the first one. Because if you want to pick up molecules from the environment, from the foodstock, then all the faces, all these crystals must expose the same face to the environment. Okay, and then the question was how you transfer information from the first crystals to the new freshly formed crystals that are formed in solution. Okay? And here I think we have a classical example of Frank model. Actually, because there are two effects which operate in unison in this particular system, which one of them enhances the formation and the other one actually promotes, inhibits the formation of the other enantiomer. And this is what resulted in the formation of these crusts. Okay, so what we did, first thing was we tried to grow crystals in the presence of R amino acids, for example, of glycine crystals in the presence of alpha amino acids, but adding small quantities of L amino acids, the leucine, valine, phenylalanine, one of these amphiphilic molecules which are in the system. And then what we observe beautiful formation of crystals at their water interface. It's a bit of an experiment. You just cool this down in the presence of L, and you can see a solution, supersaturated solution of water. You can see the formation of crystals. But what is unique about these crystals? If you look more carefully to these crystals, you can see that these crystals, which are floating in their water interface, they are just floating in their water interface. What you can see, they have a two-dimensional chirality. You see, most of the crystals have this morphology, and the other crystals have an enantiomeric morphology. Okay, if you like to see this more clearly, I mean, these are two mirror images, okay, which are not superimposable at the moment that they are floating in two dimensions. If you like to superimpose them, you have to turn them down. But if they are floating in two dimensions, you cannot superimpose them. And then what happens is you can see that, but you cannot superimpose it on the other. So this was the first example that these molecules of leucine, valine, and leucine, valine, phenylalanine, all these amphiphilic molecules, when deposited on the water, previously, what you could say by surface tension measurements, you can say 30%, 40% of these amino acids are residing in their water interface. But the structure of these molecules, the structure from the molecular level of these molecules, in their water interface was not known. And therefore now, we were very much interested to see what is their structures, because these molecules which reside at their water interface have a property to nucleate in an oriented way the crystals of glycine, which we could assume at the time that they must form clusters, very structured clusters, and these clusters are operating, they have a function. They operate as a nucleus for an oriented growth of the glycine crystals in their water interface. Okay? Well, this is again the HPLC. If you analyze these crystals, you could see that some of the ones contained the DL, like it was in this case. So what we suggested in this particular time was that if we are adding L-leucine to the solution, we might have formation of a cluster where the polar head groups of this cluster constitute the first layer of glycine. Okay? You see that because the packing arrangement, if you look at the crystal structures, so valine, leucine, all of them have some of the heterionic layers, which are formed single homochiral layers in the water interface, including the racemic valine, leucine, and all these amphiphilic molecules. So what we were proposing was that some molecules, when we have molecules in solution, the amphiphilic molecules are in equilibrium with the air-water interface. But when they reside at the air-water interface, they constitute a cluster. And this cluster, the polar head groups of these clusters are appropriately aligned for the induced nucleation of glycine starting from one of the surfaces. Okay. So you see, if we have, let's say, the R,
but you're allowing in the experiment, you only put R amino acids or S amino acids. You don't mix them.
I will tell that later on. I can mix them together. But I want first of all to do the first point to make it much clearer. But the experiment that I'm doing now, I'm putting 1% of R amino acid into the solution. Or 1% of the other. Okay, and this was actually, you see, the two-dimensional chirality. If you put 1% of L, you get 1% of R, you get R. Okay. And then what we're saying, what we expected was that these species, which are formed at their water interface, they must form a crystalline aggregate, where the polar head groups, which are at their water interface, these groups will induce nucleation. If you start with the S amino acid, they must start from the O-1 phase, and then the crystal will grow in one direction. Whereas if you start with the R amino acid, they will grow in the other direction. Okay? So, and if they start growing that way, you see they can pick from the footstock molecules of opposite energies. Okay, and if they put molecules of opposite tenderness, they enrich the solution with the green, and then the green will go back to the surface, and this green will now induce additional orientation of the next crystals, and the next crystal will grow with the same orientation as the first one. Okay? Now, we were very much interested to try to place these studies on a more fundamental basis. And at the time when we started that, there was the synchrotron, and as I say, we joined the forces with Jens Nielsen and Christian Kerr from Denmark, that they had the facilities and the synchrotron in Hamburg. And we start making experiments to try to confirm the structure of these clusters. Unfortunately, the natural amino acids don't have enough electrons to see diffraction, but we performed the same experiment by taking long chains of amino acids. We synthesized for that purpose long chain amino acids, and we found that they crystallize a nucleate lysine exactly like leucine, very closely to what happened to leucine. And we said, let us now do the structure of these clusters at air-water interface, and to confirm our proposition that these molecules form such kind of clusters at air-water interface, and these clusters actually induce the nucleation of the glycine crystal. Now, I want to point one point here, that we have not used Langmuir films. For Langmuir films, you compress them. But we were looking for self-assemblies. You just take 50% coverage of the surface. And these are self-assemblies. The molecules containing these long chains, they self-assemble at their water interface. And from these clusters, or from these self-assemblies, we were looking for diffraction from them and to assign their structures and to demonstrate that they are really playing an important role.
How long were the chains?
We took actually, in this case, we took C18, like, you know, C18, 16. But that, yeah, we actually did it with alcohols because we use also the alcohols for freezing.
Chain like in the fatty acid.
Yeah.
Because, you know, in polymer science, there's a thing called side chain crystallization.
Yeah.
Where if you make polymers with long side chain, in fact, all you need is 6 or 7 or 1.
No, we tried it actually. We tried it from 6 to 31, and we know how
it started to work at 10 or 11 or 8 or 9, because the side chains actually can crystallize.
We did this experiment from C12 to C31, and what we found that the thermal motion of the methylene groups beyond 21 is very similar to what you find in the three-dimensional crystal. But when you take the short one, you can get a kind of rotating phase of the wave, like what you find in liquid crystals.
You mean a convex phase?
Rotating
yeah,
phase.
That's the phase that Barney Funderburg studied.
But if you go and increase the number of hydrocarbons, or if you take an amide inside, because you take lysine and you attach something to lysine, and the hydrogen bond can really that.
It's really a template.
Exactly.
That you're forming.
Yeah, that's right. The template, you call it template, you call it a nucleus.
Yeah.
Because it is the nucleus which really transfers information to this part.
But the interesting thing would be also, if you had a mixture of amino acids in that.
Which one?
If you had a mixture of RNS,
you're coming to the next.
one would be excluded.
Okay, can you wait a little bit? We'll come to that part. Okay. So what we do this problem, that you take an X-ray beam, very intense X-ray beam, you count an angle which is below the critical angle, and therefore you don't have diffraction reflection of this angle. What happens is you're creating an evanescent beam on the surface of the crystal, on the surface of the water, and if you have crystallites, they diffract actually. And from this diffraction you can get the Bragg rods and you can get the Bragg peaks. And from the Bragg rods you can get the exact tube angle of this change. Very, very sensitive to the exact powder. And from the Bragg peaks you can determine the structure. Because after all these are two-dimensional. These are two-dimensional from the powder picture, because you're getting a powder picture. You can determine the structure of these clusters. And we have done this for a number of years. Our group has been really excited about this crystallography in two dimensions, and we've done a lot of studies, like ice nucleation in the presence of alcohols. You know that if you put alcohols in solution, they perturb the formation of the nucleation of ice. It's what we put in the winter in the trunks. But if you put alcohols in the air-water interface, they induce nucleation because of the same reason. You can really freeze ice at -2 degrees, which is unusual. And now, what you ask here, what will do a racemic mixture in 2 dimensions? If you take a racemate, what it can do? So in some cases you can get a racemic crystal formation. In some cases you can get spontaneous kind of separation in 2 dimensions. Okay? And we've done this, let's say, in one case, this is the diffraction patterns, seen edge on. And you can see, for example, if you take lysine, to which you attach steroyl group, you can see that the R and the RS are almost identical. Here some peaks which you have some chains in there which are differently tilted, but in principle they are very similar, and you find that this system undergo spontaneous evolution in 2 dimensions. Okay. On the other hand, if we take the glutamate, if you take the structures between glutamate and water, you can find that the structures are completely different. And if you write the crystal structures of this of the 2 dimension, you find that this is a racemic compound and this is an antimorphous crystal. And we've done this even in the presence of phospholipids. You take a phospholipid, you find three phases. You get the phospholipid, the L and the D. And you find the D and the DL. And we shall use this in the next part.
Do you know where these different features actually come from?
I think that probably some of the tilt angles, because these chains are tilted, and some of the tilt angles, for some reason, indicate there is also possibility that some of them forming a bilayer.
Forming a what?
Bilayer.
Yeah.
You see that in some of the systems, not in this, but in the other one, if you take a shorter one, you can form 2 layers. Okay. So what you say here?
Were you surprised? I mean, the picture. That's only one of the features in the upper plot, which is different from right and left. Even in the plot above for the
this one?
lysine, yes. There's only the.
It's quite surprising. You say I would expect the reverse.
Yeah.
Because if you have a mixture of 2, I would say that you might maybe form some mixed crystals, solid solutions from the system. But in this case, and we tried this in a number of them, my feeling is that once you have a monolayer, maybe you have some bilayers on top. And if you have only the pure one, it's much more easy than to form a bilayer, because if you're forming here, then bilayer will be dissolved, because you don't know whether the L or the D will be on top and the L. So this may be. But we don't have a rational explanation for whether this is happening. So what we're saying here is the following. In other words, if you have these crystals and we have elaborated the structures of the chains, they are tilted, but the polarized groups are exactly like the first layer of S of O1 minus O minus 1 in this part, and O minus O 1 O on the other, and if you take the R layer, it's just horizontal. So this confirmed what we predicted, what we anticipated from the experiments of the glycine. So the first experiment in this photocatalytic process is that assume that you have a single crystal of glycine, or a small number of glycine crystals start growing. They pick up from the environment one kind of amino acid, they break symmetry, and then the excess of the other moves to the surface, and as it moves to the surface, it actually induces the crystallization of the glycine crystals with the fresh glycine crystals with the same orientation as the first one. So this was one effect, but this was not sufficient. The second effect is a kinetic effect in the characterization of oriented crystal of glycine induced by water-soluble alcoholic acids. And this brings us to another fundamental question, very fundamental question. What is the nature of a nucleus? How a nucleus should look like when we start the crystallization? We started discussing this morning. Of course, you have many dimers and trimers and octamers and what you like, which are formed in the solution. But the nucleus and the onset of crystallization, that nucleus and this is what we assume, must assume the structure of the mature crystal. Now, well, this is a very, very trivial, if you like, assumption. The question is what you do with such an assumption. And our assumption was that if it is resembling the mature crystal, we can take the information which is stored in the mature crystals in order to design molecules with which we can control nucleation. Because what we found for the crystals, which I show you, is not only correct for the mature crystals, it should be also correct for the nucleation process, if our assumption is correct. And a way to approach this problem was to study polymorphism. Now, what happens if we talk polymorphism? Here, what we have is Na. Exactly what Jim was writing this morning on blackboard. You can have all kind of clusters which are formed. We don't know about them. But when it comes to the nucleus before nucleation, and even after the small crystals are formed, which have very high surface areas, what we're saying is that if An goes to the thermodynamically stable crystalline polymorph, then everything will move and will give out this crystal. Okay? But if we take an inhibitor which has been designed on the basis of the structure and morphology of the stable polymorph of the system, and we add to the solution, we believe that this A, B, the beta phase or the gamma phase, will start precipitating. Okay? And if we take another one, for example, we have shown this in the case of glycine, and we take glycine as 3 polymorphs. If you have molecules which affect these spaces, the crystal still can grow. But if you take molecules which cannot be attached to the surface, and for that purpose we have used hexafluorovaline, which cannot be attached to this particular O1 or O-1 phase, but these molecules, they can be attached to the side phases. So if you have, let's say, you take D hexafluorovaline, still the crystal can grow in the other direction. You will change the morphology, but you will not change the growth. But if you take DL in this case, you block all the sides of this crystalline phase, and we have seen that in the gamma phase, which is a different structure, they grow unidirectionally. They just for some reason which I cannot enter now, but you know why we study this very, they grow unidirectionally in this direction. These molecules cannot be attached on the surfaces, they can be attached only on the cap tank, which doesn't grow anyhow. So if you had 2% of this hexafluorovaline DL in the system, up to 3%, you can change the morphology of the crystal. Instead of these bipyramids, you're getting these sides are really completely inhibited. Okay? But if you go beyond 3 sides, what happens is you're getting to the gamma phase, which means the DL inhibits the nucleation, not only the growth of the crystal, but the nucleation of the alpha form. And they don't interfere with the growth of the gamma form, and therefore you can really grow the gamma form. And we have done some experiments recently that we can inhibit both the alpha form and the gamma form, and we get the beta form, which is the metastable form of the system. So now what we're saying here is some very empirical study, if you like, saying is that the onset of crystallization, actually the structure of the nucleus is very similar to that of the mature crystal, and by going to the morphology and the structure of the mature polymorph, we can design a molecule which can be used to perturb the nucleation of the more stable polymorph and to go to another polymorph of the system. Okay?
Crystal engineering.
It's crystal engineering, morphology engineering and crystal
The
engineering.
original definition.
Yeah.
The original definition.
Well, the original definition of crystal engineering was to try to find a molecule and to force it to crystallize at a given size. But this is not done on a molecule. This is not ab initio crystal engineering. This is polymorphism in like engineering. So the question now arises how this fits to our model. And I'm coming again to the Frank model. What is the original Frank model? One actually announces the formation of its own, and at the same time this one inhibits the formation of the opposite one. Right? This is actually the general definition of the Frank model. Okay? So what we're saying here is the following. for the sake of discussion, I'm taking excess of one of them, just to put it that way. And then what I'm saying is that if I take 7-3, I take 6-4, but we have taken actually 53-47, this was the minimum enantiomeric axis that is used for complete orientation of the system. What we're saying is that, say, that if you once you have achieved a certain excess of one of them, they can induce, this one will induce the crystallization of one class of crystals, of the arc crystals, whereas this one should induce the formation of the other one. But the point is, as we pointed out now, what we're saying is here, that this nucleus here, of the minor component, which faces a lot of molecules of opposite endedness in solution, which can interact with this particular surface. I mean, the major component here interacts with the opposite face of this nucleus. Then what they can do at certain concentration, they can perturb the formation of this particular nucleus. Like what we found actually in the case of the polymorphism and the control of polymorphism. Because it's exactly the same effect. If you have one crystal which faces a lot of molecules which can interact with that particular surface, they can be actually inhibitors. They will not allow the crossing of the transition state, if you like, of the nucleus to form the crystal, and therefore they are decomposed. On the other hand, they grow, they pick up the other, they pick up, let's say, the green, they pick up the green, they deplete the solution from the green in a concentration which prevents, they deplete it from the green, and then they back actually the red in excess. The red can move to the surface to enhance the crystallization, but the red which is in solution can actually perturb or can inhibit the formation of the opposite endedness. So this is an autocatalytic process, purely autocatalytic process in crystallization, which contains three different aspects. First of all, spontaneous mirror symmetry breaking by having the crystal of glycine. Let's say you have a small number of crystals of glycine which are aligned a certain way by stochastically one way or another. Once they start growing, they pick up from the footstock, they pick up one kind of amino acid, they enrich the solution with the opposite one. The opposite one moves to the surface. As it moves to the surface, enhances the crystallization with the same orientation, and the excess of the hydrophilic and hydrophobic which are formed in solution at a certain concentration prevent the nucleation of the opposite one, and this results in the formation of the crust of glycine where all the crystals contain amino acid of a single amino.
Yes. Just why only why only the S occurs in this kind of crystals, and why do you not have some
opposite one.
The opposite one that take place of the R glycine.
I'm saying the following, that there is, if you take a small number of crystals, or single crystal, we have shown that this is feasible, but we have not done, we have decided to do most of our experiment by perturbing the system with one of the enantiomers, because we wanted to understand the principles. Okay. Because otherwise you say, you do an experiment, nobody can repeat it. That's the problem. But we wanted something that can be reproducible. So if you take a small axis, which we think that has been formed because of the growth of some crystals of glycine which have grown one way or another, they actually enrich the solution with one enantiomer and deplete one with the other enantiomer. The one which is in excess in solution, which is in equilibrium with the interface, creates nuclei of the same endedness, which nuclei of the same endedness is the major component here, and they induce the crystallization. They induce the crystallization of glycine crystals with the same orientation as the first crystal. They transfer information. Furthermore, if the minor one, they also can start nucleating. Okay, but I have shown that if this nucleus, especially the surface which are exposed to the solution, this surface here, resembles the mature crystal, we say the excess of the red one, which are formed in solution, and we found that if you have 5347 in a certain composition, they are sufficient to inhibit completely the formation of the crystals of opposite elements. And therefore this is exactly in accordance with the Frank model. That one which is in the solution with air-water interface enhances the growth, and one which is in solution perturbs the formation of the unwanted one.
I know that Donna is polarizing here, and that she is controversially discussed, but isn't it so that these old things like Oswald's ripening,
Yeah.
and with the reverse one that the small nuclei are dissolved in small,
What is it?
explains it wrong.
Oswald ripening.
Oswald ripening explains that in the saturated solution,
Yeah.
large crystals
Always grow.
will
Always grow, yeah.
while smaller crystals
Will
nuclei,
disappear.
they can
Disappear.
disappear and reappear. And
No, they will disappear, because if you take this,
they dissolve faster.
they dissolve faster, and then
Right.
if they dissolve faster, they
Oswald
grow.
ripening.
Yeah, this is also ripening.
So the kinetics, it means just Oswald ripening.
Yeah, but in this particular case, what you're saying is that the small one will disappear and the large one will increase. That's what you're saying.
Yeah.
Yeah, but in this case, if you don't have, let's say, the amino acids which inhibit the growth of this part, which is in addition to the osmolarpinic, maybe the osmolarpinic may be also playing some role, I don't know, but here it's quite clear that if you take, let's say, only let's say, DL leucine, you take DL leucine, which you create crystals on both sides here, and in solution you are getting only excess of one of the amino acids, you get the same result. Because what happens is, you have some elements here of oswald ripening, if you
I'm
like.
not sure whether we are entering a semantic discussion.
You see, oswald ripening is a macroscopical phenomenon. It doesn't enter to the molecular level.
Crystallization is a microscopic phenomenon.
Yeah, but you can explain for crystallization on molecular level. Because the mechanism of inhibition and the growth is done on the molecular level.
Yeah. As I said, no objection.
I think that what I'm saying is, in order to answer your question, if I'm not using here the amino acids under this control, this regime, I'm going to get small and large crystals. In order to get large crystals, according to the oswald ripening, you have to wait a lot to get equilibrium, thermodynamic equilibrium. Here, this is done under very fast conditions, which are far from equilibrium. You see, I think this is the very point which was raised this morning. Also ripening is a thermodynamical process. This was the big discussion between Ribo and Zona about the sodium chloride example.
Well,
And
that's
yes,
just a whole discussion.
no, I think this is very important what you're saying. Because also ripening is under those conditions which are thermodynamically controlled. Now, but the small one will disappear because they have a larger surface area, and therefore they're less stable than the large one, which has a smaller surface area. Then it will take some time until the small one will disappear and the large one will grow. But in this case, and we have shown that, like with the polymorphic studies, that if you have the additive, if you have the additive, you are preventing the formation of the other one. Kinetic, not by thermodynamic control. But if you, maybe you're right, but I cannot exclude completely some kind of thermodynamic principle, something which takes into consideration also, right? But I can be sure that you need the additives, otherwise you need the inhibitor, otherwise you can.
Where's the exclusion? If you take leucine
Yeah,
and crystallize it,
yeah.
maybe I missed this point. Does it form a conglomerate?
No. Leucine forms a racemic crystal. It's very difficult to solve.
That's where my question comes from. Where does this? What is the structural basis? Do you have any idea where what the structural basis is of the exclusion of one enantiomer. In other words, why, when the R is in excess...
Yeah, I understand your question.
Why is it excluding...
I tell you why.
Because in the regular crystal...
I tell you why. Because we have computed how much energy it costs for opposite enantiomer to be attached on the particular surface. And it's more than 100 kilocalories.
Okay, then what you're saying is that this type of an aggregate, this sort of quasi-crystal, which you're going in a Langmuir logic...
It's a mixed crystal.
Well, that it's a much more selective process than the normal crystallization.
Not necessarily. Why is that?
Because in the normal crystallization, you can fit both enantiomers into the...
No. If you look on the crystal structure on the molecular level, you cannot fit less than in the crystal of the glycine. Because it's still a crystal of the glycine.
Leucine.
No. If you take the crystal of...
This is leucine.
No, this is glycine.
Lysine?
Glycine, yes. This is glycine. This is glycine. I take here leucine 1%. And this is glycine.
Oh, I see.
And then what happens is that if I get crystals of one kind or the other, and I think the amino acids which are here, actually they prevent the nucleation of the
That's
crystals.
involving crystals from
Yeah,
that's
that's right. But I can after that I can convince you that it is the inhibition of nucleation is very, very important. It's maybe you add some elements of also rapid because they operate in the same direction. But I think that the fact that they are here, actually they really operate like they've shown this in crystal polymorphism. Okay. Okay, this is the problem. Okay. Therefore, I think that can be explained by applying the classical Frank model. The hydrophobic clusters at the interface induce nucleation of the glycine crystals in the desired orientation, whereas the water-soluble amino acid formed in excess operate as nucleation inhibitors of the nucleation of opposite orientation. So this is, I think, that one part of the lecture.
Interesting. That's first of all, thank you, Meir.
The next lecture I would like to go to the peptides, because as I say, what are